Yes, my name is Michael Amundsen, and this is how you find me. You can find me on GitHub and Twitter and LinkedIn, and it's probably the best way to locate me because I travel quite a bit. This year, maybe 40 weeks traveling somewhere. This is my first visit to Ukraine. I'm very excited. I'm very honored to be here to talk with you today. You can also find me at this webpage. This will be in the slides. I travel around a lot, visit lots of companies, do lots of training and advising on microservices and enterprise and transformation and APIs and things like that. And you can find out where I am. I have a calendar there. I'm sponsored on this trip partly by API Academy, which is a really amazing group of people scattered around the Northern Hemisphere. We visit companies all over, so I have colleagues that also travel almost as much as I do, based in Zurich and London and Vancouver and Paris, and I'm in Kentucky in the United States. So bourbon, right? Whiskey, Kentucky, yes. This is a book that our team did about a year ago. Microservice Architecture for O'Reilly. CA sponsored the book. The company CA sponsors it, so you can download an ebook copy for free. You can also purchase a hardbound copy, or if you really want to just purchase a copy rather than download the PDF version, you can do that at O'Reilly as well. And we just released this week, actually will be in print next week, a book on APIs. I'm going to talk later today on continuous API management. So I'll just mention this. This is another book project. This is one of the things I enjoy so much about working in my team, is we get to work on projects like that. Okay. So this idea of microservices and types of microservices. What are we going to really talk about? So one of the first things I want to mention is this notion of programming the network. When you're dealing in microservice, you're not programming machines. You're actually programming the entire network, the global network. That's much harder, and the problems are different. They're very different than machines. So we'll talk a little about that. Then we'll talk about this notion of microservice. Why is it popular now? Is it different than what we've done before? And if so, why and how? And then I'll break down this idea of 3 different components types. You can think of them as 3 flavors or as 3 behavioral patterns, and how you can identify them and how you can use them in your own application, in your own network. And then I'll talk a little bit about these things called stability patterns. Does anyone know this? Michael Nygard? Yes. We'll talk about his book, and I really encourage everyone to get a copy of this book. It's now in its 2nd edition this year, and we'll talk about it a little bit. And we'll apply those patterns to microservice types. Why would we want to have some of these stability patterns, and where does it work? So we'll apply those, and we'll find out how we can start to make our services more resilient, more recoverable, more visible, more observable, and more powerful. And then finally, if we have some time, I have a little, wait, there's more Steve Jobs, one more thing kind of thing that we might add if we have time. Okay, so let's start with this idea about programming the network. So as I mentioned, I do a lot of traveling. This is my normal commuter transportation in the morning. Where I live in the US, I'm about an hour or 2 from all the major cities on the East Coast and in the Midwest. So Chicago and Atlanta and New York and all these places. So I often can commute to work. Yes? We have some trouble. Okay. You see? So I can often commute to work on a plane about at the same time frame that several people in the US commute in a car in an hour or so. But I also do another kind of traveling, and we all do this other kind of traveling, and that's traveling in the network. It's actually traveling from server to server and place to place. And we travel great distances. One of the really powerful elements of the World Wide Web is that we can travel anywhere in the world. Sometimes we don't even know where we're going to end up, which server we're on, but we get to be there. And that ability to travel the network means that we need to understand how that network is different than any one particular car or plane or machine. And that means programming it. In programming a network of machines that you don't own, that you didn't write the code for, that you don't decide if they're what language they're in or whether they're reliable or up and running, that's our job, right? We're no longer controlling things. If you were here in the last talk, we had a nice slide for a moment where sometimes we think we're God, but actually we don't have any idea of what's going on, right? And when you're in programming the network, most of the time you don't have any idea what's going on behind the scenes. When I go reach from one machine to another, I don't know how many different hops I'm making. I don't know how many machines that one that I'm trying to get to also depends on. I have no idea. And the number of hops will change from minute to minute, and the number of machines that it depends on may change from month to week to year. These are things we don't know about, yet we need to be operating in this space. So sometimes things don't go well, right? Even when you're dealing with one machine, things can happen unexpectedly. In real life, however, we deal with these unexpected things all the time. Traffic jams and a closed store and not enough money to pay at the machine and the machine is broken. We deal with all of these things all the time. But when we write computers, we try to pretend that they don't exist, that these things don't break. But of course they break all the time. This is what we program. We program all these connections. And what we can do is we can get close to what we want to do. We can get close to how we would like them to behave, but we can't always be sure. So Pat Helland, who worked at Microsoft and Amazon and now works at Salesforce, has this great line. There's no simultaneity at a distance. Right? Do we know what? Can we think about what this means, right? So you think about the fact that there is distance involved. That means that there's time involved. There's even time involved between when I speak and when you hear it at the back of the room, but it's so very small we don't care. But there's lots of distance in the universe. When I see a star up in the sky and I think it's beautiful, what I don't realize is that star died billions of years ago and the light is just getting to me now. Right? In fact, what I'm doing is traveling back in time when I see the light. So when I go to a website and I say, how many books do you have in stock of that great book by Mike Amundsen? Yes, 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 I have 5. By the time the message gets to me, there are not 5 in stock anymore. Right? This is what we deal with all the time. We'll like to imagine that that distance doesn't exist. Even worse, most of our programming tools make us think that distance doesn't exist. And yet it's essential for us to be successful. The way Pat Helland talks about this in his paper is inside the machine, inside our laptop, inside the server on the rack, we have these idea of sort of the Newton rules of physics. For every action, there's a reaction. We can see every moment. There's a tick of a clock inside the machine, and there's an instruction every tick, right? So we have all these things. We can say if, then, else. We can start a transaction and end a transaction. We can do all these things because we're living in Newton's world where it's a machine, it's a clockwork. However, when we step outside that one machine into the network, it's a totally different set of rules. Now everything is relative. Now what I see on the network is not the same thing you see from the other end of the network. Or if we see it, it may not even be happening at the same time. A great example about this relativity that exists on the network comes from the growth of HTTP. In the beginning, HTTP caching was an absolute number. Cache until this time on the clock. What they didn't understand at the time was that everybody's clock wasn't set the same. Sometimes I could send a message, say cache this until a certain time, and by the time it got there, that clock was already like past that time. So I wasn't caching at all. So how did we solve this problem? We created relative caching in HTTP. So HTTP 1.1 has this notion of you cache for 30 seconds. I don't care what time you think it is. I don't care how long it took to get to you. Hold it for your 30 seconds. Relativity. So thinking about this in relative terms gives us a new set of challenges for programming. So again, Helen talks about this idea of speed of light. By the time you see an object, it's not there. By the time you get the message, the data has changed. So we can have things like services and transactions and locks, and they're all dependent on simultaneity. They work on one machine. If we try to do a two-phase transaction against several services, that's impossible. We can approximate it, but we can never actually do that. And that changes the way we're going to think about how we program the network, because the notion of now between services is very different. Okay? So now that's our challenge. Now, the idea of this notion about networks, it comes from a great set of fallacies by Peter Deutsch, dating back into the early 90s. And you may have seen many of these. The network is always reliable, right? Latency is always zero. Bandwidth is always infinite. We know these fallacies. I have these posted on my wall next to my workstation to remind me. The problem is, of course, none of this is true, yet we almost always behave like it is true. And this is what gets us in trouble. We have to remember there's always latency. The network is never reliable. Bandwidth is always constrained at some point along the network somewhere. The network is never secure. We can never trust the message we're getting from the other party explicitly. Even if you're inside the firewall, it's a bad idea to trust that. So we have to sort of change the way we think. Do we know this Rich Hickey? Closure, Datomic, anybody heard of these? So Rich Hickey is really sort of the mind behind this. And Rich has a wonderful way of talking about the challenge of the network. He calls it system programming rather than a single program. So instead of thinking about application libraries and thinking about core libraries and runtimes and language primitives like if, then, else, and types and so on and so forth, he says we need to start thinking about services. Application libraries are replaced by services. And simple services become this core set that we all use. And that the language primitives of the network are the protocols and the message formats. There are no objects on the internet. There are only messages. And those messages get serialized from objects and deserialized into messages. But it's the messages that we share. There are no types. There's no floating type on the internet. That floating type only exists on the machine. It gets turned into a string and then passed around. Or it gets turned into a binary number. Binary representation gets passed around. So programming the network brings us challenges, and that lands us directly to this notion of microservices. So Martin Fowler has this great definition that most people use when we think about microservices. Developing a single application is a suite of small services running in their own processes and communicating over lightweight protocols or mechanisms. That's a pretty good one. It's a mouthful, but it's pretty good. I like this description from the year 2000. Does anybody know this person? Roy Fielding. Roy Fielding is the one who caused us to talk about REST, right? He says his idea of system architecture emphasizes scalability of interactions, generality of interfaces, independent deployment, and intermediaries. On the network, I can't tell you when to launch your server or when to refresh your server, right? We have to do it in a way that doesn't hurt either one of us. Generality of interfaces mean I can't tell you what your interface should be, and I can't change my interface and expect you to change all of your work just because I changed one thing. So we use things like HTTP protocols or FTP or IRC or all these other standard general interfaces. I like this one. This goes back to the late 90s. A universal link system where generality and portability are most important. We've been talking about the same thing for decades. So what are the characteristics of a microservice that we can really discuss, that we can talk about? This is an easy one. Make each program do just one thing well. And whether that one thing is manage users or that one thing is deal with search for users, it's just one thing. And that has to do with the idea of boundaries and several other things that we don't have time to talk about. Eric Evans has been talking about boundaries with his domain-driven design for about 10 or 12 years now. So we have lots of material that we can lean on. We can expect the output of every program you write to be the input of some other program. Right? That's a key element. When we write the software, we expect it to be, its output to be consumed by some other piece of software that we didn't write. Right? We have this idea of designing and building to be tried early. Build a small thing so that somebody can try it, so you can learn from it. Build it over and over and over again. This is another habit that we're developing in microservices, which is to be repeatable and to be rerunnable. And finally, we have this idea of using tools to lighten the task of doing the work itself. We can use lots of tools, just like there are compiler tools for machines. There is a thing called the Chaos Army. Does anybody know the Chaos Army from Netflix? Right? Or there's Etsy. Do we know this Etsy shopping service in the US? They release to production 40 times a day. 40 times a day. They build this huge infrastructure to make sure that that's safe and easy to do. They're building tools to make it easier for them to actually solve their problem. Now this list, do one thing well, output is input, designed to be tried early, use tools to lighten the task. This may look familiar to some of you. It's actually the operating principles from Unix from 40 years ago. Right? So we're not doing anything new here, but we're doing it at a different scale. These Unix principles were for programming one machine. The original idea behind Unix was that you didn't need applications, you just needed services that you could stitch together with batch programming, right? So there wouldn't be a word processor anymore. There would just be Edlin and some other services. So you can set and awk and grep your stuff, right? Of course, it didn't work out that way, but that was the ethos. So the same thing we're now talking about doing at the network scale. All the things that we've been talking about for 40 years. The good news is we have lots of people who've already done the work, done the research, that know what works. We can stand on the shoulders of giants. So this is the way I talk about services, loosely coupled, running in an engineered system. Doesn't matter what language, doesn't matter what protocol, doesn't matter what message format, none of that matters. What matters are loosely coupled and engineered system. What does loosely coupled mean? It means you can release without having a meeting. It means you get up today and you test and you know it's stable. You can release it into the network without hurting anyone. That's loosely coupled. That's the way the World Wide Web works. I can put my server on the web without asking your permission. Right? I can make changes. I can move the links. I can move the forms without asking you first or waiting for you to update yours. That's a loosely coupled system. An engineered system, that's DevOps. That's this process where we build step by step and it's repeatable and monitorable and observable, and we can roll back to the previous version and we can test it to make sure that it doesn't break the old versions. So those two things, this ability to release when I'm ready, not when you're ready, and to make sure that I release it into a system that protects itself from me, as well as from everyone else, that's a good way to think about microservices. Okay, so that gives us this idea about what microservices should be about and how we can think about them. How can we break this down into something that's tangible and useful rather than just conceptual. And this is where I lean on this notion of trying to come up with ways to think about them in very concrete terms. So I'm going to introduce this idea that there are only 3 possible types of microservices. Now, that's probably not true. There's probably 4. Wait, 7? No. 6, 12? It kind of doesn't matter, but if we start with something tangible, this will give you some ideas about how you can start thinking about the services you're building. So I want to talk about them in 3 ways. What's typically referred to as a stateless service, some kind of persistence service, storage, and some kind of aggregator service, or orchestration, or choreography, or something like that. These are 3 fundamentally different ways of thinking about a service, and they have different risks, different responsibilities, and they can perform different things. Let's talk about the one that I'm calling stateless. So these are simple processors. They're converters, translators, mathematics, language translation, weights and measures, simple tables, lookups, things like this. Right? They're very, very simple. They have no dependence on any other service. They can operate on their own just fine. They don't have any other connection. They don't have any other dependence on some other storage service or some other network service or anything like that. They're just by themselves. They have no local storage to speak of. You give me a number, I'll convert it into another number, and that's out the door. I may have some things in memory, some lookup tables. I may have some mathematics, some matrix math to do. Maybe I'm actually computing interest, carried interest, or net present value, or mortgage loan values, or risk analysis. But I don't have any other data that I need to depend on. I just take your information and produce new information. This is the most common microservice component example people think about and people talk about. We're going to do a stateless microservice. Turns out it's to be the least useful service. What am I going to do if it's not connected to anything, if it's not connected to data, if it's not connected to existing customers, if it's not connected to any other bit of information? I had this tiny little island. It's useful, but not very. So it has no shared state with anyone else. I don't have to remember from one iteration to the next who you are. It's easy to replace. I can simply swap another one out. I can write one in Rust and replace that old Node.js version anytime I want, right? Nobody's going to care. Nobody's going to notice. It's also easy to scale up. If suddenly everybody wants to know how to translate English into Ukrainian, I'll just have lots of servers that answer the question, right? It's easy. It's simple. There's no shared storage. It's just more servers. And I can put them all over the world if I want to. Doesn't really matter. This is what we think of as ephemeral computing. It's not connected to any storage medium or anything else, and I can spin up just as many as I like. AWS would love to do lots of them for you, right? Or Heroku, or Azure, or Google, or anybody else. These are easy. So what does it look like? By the way, this is not real code. This is just kind of some pseudocode. I need to do a conversion. I'm going to get some request. I'm going to convert that value into something else, and I'm going to send it to response. There's nothing else to think about. No storage, no nothing. Okay, let's think about the second one, persistence, data storage. So now I have simple local storage that reads and maybe writes data, right? So I'm at least dependent on disk I/O. I'm dependent on my local disk, or some server that's next to me in the rack that's actually running the MySQL server or something else, or some document database or something like that. There's possibly, I'm dependent on some 1U or some rack of storage in the same sort of space, or a virtual machine or something like that. This is very commonly needed, but it's not the easiest to implement. There are lots of challenges here, because often there are lots of people trying to read, and lots of people trying to write. And they're doing it on a network that's very unreliable. So what if they never know if it actually completed or not? Do they do it again? How do I handle people trying to do things twice? Do I let them? Should I prevent them? There's a lot of stuff that goes into this. Often these are referred to as a system of record or a source of truth. This is the one database where all the users are. There's only one database in the entire planet. for all of time, and everybody has to read that one, right? It's just one single thing. It's relatively easy to scale for reads. We have this pattern called the CQRS pattern, Command Query Responsibility idea, where I can have lots of servers for queries because they're not going to really write any data, so I can actually optimize them for queries. However, when I'm talking about a service, now there's no two-phase commit. I can't read from the user database and then read from the sales database and then read from the invoice database and then open a transaction to write all of them and then close the transaction on the last step. That's not going to happen. I don't even own those servers. I don't know where they are. There is a thing called a saga pattern. Has anybody heard this before? Molina's saga pattern from the 1980s. This was designed in the 1980s when they were afraid that SQL, relational databases, wouldn't scale well enough on mainframes. So they started to design these ideas about how can we super scale transactions. Chris Richardson, who's done a great book on microservice patterns, and he has Microservices IO website, talks really well about how to implement the saga pattern. So we often refer to this as durable storage. And you can sort of imagine already what challenges you're going to run into when you're trying to do durable storage. So I need to write some local storage. Who knows where I'm getting the data? Who knows what actually happens behind the scenes? You may send me a transaction where it's customer information and their contact information and some sales update information. Maybe that's going to 3 data storage devices, right? But you don't know that when you send me one message. Who knows what goes on behind the scenes? Maybe it's 2, maybe it's 3 today, maybe it'll be 4 tomorrow. And when you read from one place, you don't know how, when you make one read request, you don't know how many places I need to go to get it. And that may change over time too. And you as the reader shouldn't know anything about that. You should just know I send a message and I get what I need. So finally, let's talk about aggregator services. So aggregator services depend on other microservices, right? So maybe there's another data server here, and there's another persistent service here, and there's a couple of stateless services over here, and I need to put them all together to solve a problem, to compute a value, or to update some information. Often they're very network dependent, so I'm not just dependent on each machine, but I'm dependent on the network that's running between those machines. If it turns out one of those machines is in Australia, one of those machines is Ukraine, one of those machines is South America, there may be some differences in the network bandwidth quality in those various locations. The network may go down in Brazil, but the rest of the system's up and running. What do I do now? Usually there's also local I/O dependence too. Maybe I've got local storage that I'm using to sort of cobble together things that I get, do some of my own computing. Maybe I'm actually storing cached copies of various services so I can actually do the work myself. This is often the one you really want. This is the service type you really are hoping for, combining lots of things together. It is the most challenging. It's the hardest to build. It's the hardest to protect. It's the hardest to scale. It's the hardest to secure. There's all sorts of challenges here. Yet this is the one we all want. This is the one that would make it great, right? Because then I could sort of change any part and nobody cares. Now, big question when you're coming into aggregation is whether you're going to be able to have to deal in sequence. And in other words, I have to call server A and wait, and then call server B and wait, and then call server C and wait. Or if I can parallelize them. If I can call A, B, and C together and then wait for them all to respond. Instead of doing it sequentially, now the longest wait time is the slowest service, not the combined time of all the services. Maybe I can parallelize 2, but one of them I'm going to have to wait in sequential. I'm going to have to actually call to get a number back so I can use that ID to look up the other 2. You have to know this when you're doing the composition. However, the services you're composing rarely understand what you're doing. They don't need to know. Timing is everything. How long it takes may be too long to wait. Now what do you do? If somebody doesn't respond to you in time, what do you do upstream? How do you answer? Think about the fact that you may be calling a service that's actually calling some other service? What if that service is slow? There are all sorts of things that you don't control. It should be easy to scale, but this can get really tough really fast. We often refer to this as choreography or orchestration or workflow or some other thing like that. In the past, we've centralized all this into one place. In enterprises, we use an ESB or some other tool like that, or in lots of other organizations, we just put it all in one big local network and we don't think about the distance. If we start breaking that up into parts, we're going to have lots more challenges. So I actually need to interact. I need to gather resources from lots of places, and I need to interact safely and get that service list and update all of the data and then just say thank you very much. But there's lots that goes on behind there. So we've talked about ephemeral services, durable services, and this idea of workflow or choreography. If we can isolate the way each one of these behave, we can start to create reliable, resilient versions of those. And we can do it in a way that's efficient, that doesn't cause us to do a lot of extra work for nothing. And that means we need to figure out how the network affects each one of these. And that's where I talk about this idea of Nygard's stability patterns. Michael Nygard is this great developer. He actually works with Rich Hickey right now in the datomic space and some other language spaces projects. And I love this line that he has: bugs will happen. They can't be eliminated. They must be survived. Right? This is very important. When we test, we should be testing for survival, not testing for bugless code. This is especially true in the network because there are so many things we don't control. He's got a great book. We talked about this earlier. Release It. I encourage everyone to pick up a copy. It was written originally focusing a lot on programming a low-level network, things like TCP/IP. So there are lots of things in there like that, but don't let that discourage you. If you primarily work in the application level space rather than the transport space, there's lots of great material in here. I'm going to focus on his stability patterns. He has a whole other set of things called capacity patterns, which I'm going to skip and not mention today. And there are lots of other things in the book as well. So I'm going to focus on several patterns that he has in his stability section. We've recognized some of these: timeout, circuit breaker, bulkhead, steady state, and fail fast. Now some of these we've heard, right? Timeouts and circuit breakers, maybe even bulkheads. Some of this maybe we haven't. The last one is handshaking. We'll talk about that. So let's talk about each one briefly, get an idea behind it. What is the timeout pattern? It's simply a mechanism to allow you to stop waiting for an answer. When you're working on the network and I ask for you for the database records, I've only got so many milliseconds. If you don't answer me, I'm walking away. I don't have time for this. I got problems of my own. I can't wait for you. So that's the first step in the process. You need to make sure that you always program it in a way that you can simply walk away. If we write some tightly bound code where I'm stuck and I can't cancel the request, then the whole network's going to fall apart. So timeout's the first one. It's a simple example here where I want to actually cancel a service, send a sig term to terminate the signal. If it doesn't work, I'll wait for a certain amount of time, and then I'll just simply hard kill it. I'll just forcefully shut it down. This is my way of not getting stuck waiting around for somebody who's late. That's very different than a circuit breaker. A circuit breaker is a way for us to degrade functionality when we're under stress. Speaking of under stress, let me just take a little drink of water here. Circuit breaker is this notion that when things aren't going well, I'm going to go ask somebody else. So normally the circuit is closed, everything works just fine, but then suddenly somebody starts misbehaving. I'm going to flip a switch and say nobody should be talking to this service anymore because it's unreliable. Mike has a problem. I'm going to go talk to Mary instead. And then after a few seconds or minutes or whatever the thing is, I'll try Mike again to see if Mike is healthy. And if Mike is healthy, I'll say thank you, Mary, for your help, and I'll start working with Mike again. right? So this is a pattern to protect me from when a certain service is unavailable. What I need is an alternate. I need a circuit breaker. I need either a copy of that service or some other version of that service or a copy of the records that service used to use. There are a couple of different steps that you can go through. Eventually, I probably have to just send a 500 if I don't have any of that. Usually there's 3 levels you can do before that. That's a little different than a bulkhead. A circuit breaker is a complicated thing. A bulkhead's pretty simple. It enforces the principle of damage containment, what Subbu Alamaraju at Expedia calls limiting the blast zone. When something bad happens, you don't want to ruin everybody's day. You want to kind of contain it as much as you can. So we have 2 services, foo and bar, that are dependent on BAS. If BAS goes down, both of them are in trouble. How can I solve this problem? I create a pool of BAS servers, so if one of them goes down, there's still another one that's still working. Or I put 5 of them in, so the odds of 4 going down or all 5 going down are low. In other words, I take on my own. It's a vital service. I want to make sure it's up. I'll run several copies and put it in a hunt group. Right? Steady state. This is an interesting one. I like this, and I didn't really understand it until I read Michael's book. Systems should be able to run indefinitely without human intervention. John Allspaw, who is the head of the service reliability for Etsy, has this test where when he takes everybody, he says, now, before you come to class, all of you DevOps leaders, start your system up from scratch. And then you're not allowed to touch that system or answer any other call. How long will it continue to run? How long is it before somebody's got to clear a log or answer a question or restart a service or some other manual thing? Most of us have all these little manual things that we have, and they can get us in trouble. It's often called fiddling. Somebody has to type something to keep the system up. At AWS last year, somebody had to type something to keep the S3 buckets up and running. They typed the wrong thing and took all the S3 buckets offline in North America. Oops. It's because a human was fiddling, a human was typing. That's a sign of a problem. Purging data with app logic. I'm writing all my logs. How many of us done this? I'm writing all my logs to the server, and I put it into production, and I forget that I had the debug turned on. So I just keep writing all these logs and writing all these logs, and suddenly everybody's beeper goes off, everybody's phone goes off. What's wrong with server 3? It's out of memory. It's out of disk space. Oh, yeah, that's right, I forgot. Right? Systems need to protect themselves. When I start running out of disk space, I need to start automatically purging records. Right? Sorry, they got to go. You know, I got to keep running. I don't care about your history. I'm going to protect myself. Limit caching, same reason. I don't want to run out of memory space. I'm going to start evicting things. Roll the logs. So maybe I've got a log service. I'm shipping all the logs off to another server somewhere. Suddenly that server starts misbehaving. What am I going to do? Well, that's a circuit breaker situation. If I can't find somebody else to send the logs to, I'm just going to start deleting them. Because it's more important that I stay up and running than you have the history. We have to design this kind of behavior in. Okay, and then fail fast. Fail fast is the opposite of timeout. I learned this from Netflix. They do this at Netflix. So they make an internal request. I need you to get the list of all of Mike's recommended movies. You have 200 milliseconds. And then I get the request, and I see you're telling me I have 200 milliseconds. I know from history this is going to take me 250 milliseconds. So what am I going to do? Am I going to go run it anyway and have you walk off and leave me hanging? No. I'll say, can't do it in 200. You're on your own. Right? I'm not even going to run the request. Lots of organizations run into this situation where something goes down and then they have to get everybody up and running again, and everybody up and running again collides with everyone else trying to get up and running again, and then everything crashes again. because they don't have this notion of fail fast. They say, no, I can't solve that problem. I'm not going to get a backup of a bunch of requests for login. I'm just going to tell you nobody can log in until I solve my problem. This is sometimes referred to as back pressure too. So what I want to do is I want to say, give me a time budget, and if I can't meet the time budget, I'll just say no, and you go on. Treat me as a circuit breaker, go to your alternate source, whatever you need to do. And then finally, there's handshaking. Handshaking is all about letting people protect themselves by throttling load, by telling people what's going on. And in TCP/IP, there are all these extra terms that are called acknowledge and send and ACK, and I just sent you a packet, and are you ready to get a packet, and all these other things. We don't have that at application level. So what we do to replace handshaking at application level is we have health checks. Right? In health checks, I could expose a port or an endpoint where you can get a health check on me. Well, not just what my memory is or what my disk space is, but what's my average transaction time? What's my error rate? And there are whole parts of this, RED and I forget the other one, RED, rates and errors and duration, responses, errors, duration. There's a whole set of patterns that help you get a health check. And you can actually put me in timeout, put me in jail if my health checks are bad. I won't even use Microservice. So health checks let me ask ahead of time before I even connect with you. Then finally, I'm going to add the cache pattern from capacity because the cache pattern is really powerful. You can reduce load on a server and cut response times to a fraction when you use a cached copy. What's the fastest, most reliable network transaction? One that doesn't involve the network. Right? Use the copy you have. We all have this power. HTTP has a fantastic set of tools for doing expired timeouts and relational and e-tags and all sorts of other things that we can use to improve the network efficiency. So we can just check the cache first before we go on to make the request. Okay, so how can we put these two things together? How can we look at services and stability and make sense? So a stateless service. What if it takes too long? That's easy. I'm sorry, it's going to take me too long. I'm just not even going to do it. I'm sorry, you asked me to figure out the net present value of the world economies of all of South America. I can't do that in 2 minutes. So you're done. Go away. I can protect myself. So we'll get a little bit different when we talk about persistent services. What if it takes too long? What if the dependent service doesn't respond? The disk doesn't respond? What if this disk is down or unavailable? What if I've overflown on data or logs or some other thing like that? There's all sorts of things I need to think about. So I can fail fast, but I can also time out. I can time out on the people I'm trying to contact. I can use a circuit breaker and get the data from some other location, which might even be my own cache. I have to perform my own steady state work to get rid of logs and protect the disk space I need in order to operate on my own. And then for aggregators, we can do all of those things. What if it takes too long? What if a dependent service doesn't respond or it's down? What if storage overflows? What if it's unhealthy in some kind of way? What if things spike for some particular time? Now I have to do all of those things. I can implement the fail fast, the timeout, the circuit breaker, the steady state. I can check for health, and I can actually put things in bulkheads to make sure that they still survive. These are all things that we can start to apply. Often when I work in a group, we start talking about putting services together, we label them, and we already know what kind of mitigators, what kind of stability patterns I need to implement for that service. And many of these stability patterns aren't actually done in code in the service. There's a sidecar that does that work. There's a gateway that does that routing work and all sorts of stuff like that. So I don't need to do that on my own. As a matter of fact, when you think about the way serverless works, it's trying to handle most of those things for you. This is not something new. Now, this may seem like a lot of clutter. A couple of lines may turn into a whole bunch of code. And I love the way Michael Nygard talks about this. Is all this clutter really necessary? It turns out you spend more time mitigating the network than actually executing the job you were requested to do. That's real life. You spend more time navigating traffic, trying to get everything ready, get everything packed for your trip, getting there, getting through security, all those other kinds of things than you actually do getting flying on the plane. So clutter is the way we work. All right, so I need to wrap up. We've talked about this idea of applying patterns. You apply fail fast to stateless, timeout circuit breakers and steady states to aggregation, and the whole list when you come to that aggregation pattern. Okay, so I got 5 minutes left. Let me see if I can do this next section in 5 minutes. Sorry about that. Okay, let's see. So there's a couple of things worth mentioning. The difference between interop and integration. Integration is when you subsume a system. Interop is when you're peers. On the network, you're peers. You need to treat everybody like adults. You need to treat everybody like they're protecting themselves. You're not in charge of anyone else's life. The way you integrate is through understanding, is through semantics and messages, not through data types, not through database models, not through source code. Just because we're all written in Node doesn't mean we understand each other. So communication through the semantic layer is really important. We've already talked about the importance of time and distance when we talked about Pat Halland. I love this line from Alan Kay. He's sorry that he coined the term objects. The big idea is messages. Messages is what we send over distance, not objects. I don't slice off an object from the disk and hand it to you. I convert it into a message and send it, and you're supposed to do something with it. We've talked about programming the network already. The network offers some really important challenges, and one of them is the idea of safety. How do I know that this request is safe to execute? If I execute this request, is it going to change data, delete data, move data? It turns out that in HTTP, this is an understanding built into the protocol. So there are safe actions such as head and get, and there are unsafe actions such as put and post and delete. When you're using a protocol that doesn't make it clear which items are safe and which items are unsafe, you may get confused and execute the wrong thing or do the wrong thing twice. Now I know if it's safe, if I didn't get a response, I can hit it again and I'm not going to be deleting anything. I'm not going to be updating anything because it's safe. But if I'm unsure about that, now I have to do that in some other kind of way. This is going to be one of the big challenges in reactive systems, WebSockets and other systems like that, where they don't make it clear in the protocol whether it's safe. And the other one is idempotence. Does anybody know this word, idempotence? Right? It's from the idea of potent strength and idem repeated, right? Repeated over and over, repeated strength. To use HTTP again, when there's a form element that has a get on it, I know that I can repeat that over and over, and if I don't get a response, I'm not going to change anything. But when there's a post on it, it's a totally different set of problems. If I'm doing a post and I never get an answer back, now what? Do I do it again? How do I know? Maybe it made it there, but the response didn't make it. Maybe it never made it there. If I'm doing a put, however, a put is idempotent. A put says you can repeat this safely. So if I don't get a response from a put, I can wait and I can do it again and know that I won't double bill your account. That's why put exists. With post, I'm never sure. With put, I'm always sure. That's the guarantee. Almost all the automated services that I build use put and not post for that reason. Because if something goes wrong on the network, I can safely repeat it. So we've talked about integration and interop. We talked about time and distance and safety and idempotence. So what does that add up to? We need microservices so that we can program the network. It's really the only way to program the network. That means we have to think about all the interaction patterns, the network effects of all these patterns. It means we have to think about what we pass between parties, what we understand. We have to think about the role of time and distance. We have to constantly remind ourselves of the challenge of the difference between a machine and a system, between a program and the network. That's a lot to think about. The good news is we can think about it in small chunks and small pieces. I like this quote from Paul Clements, another great software architect that helped build a lot of the foundations. The best software architecture knows what changes often, makes that easy. makes that safe and easy? What part of the system changes? Let's make that easy so it's not, it's hard to screw up and it's easy to build. So I want to say thank you very much. Yakuya, thank you. Thank you very much. If you wish, you can subscribe to my newsletter. It'll be in the slides. And I want to just say thanks again. I'll be around here the rest of the day. I'll also be doing another talk at the end of the day, and I'll be here tomorrow. So thank you very much. Thanks. Thanks.